In the name of the Almighty, the Compassionate, the Merciful. Now we start our lessons in calculus. Since our functions are defined over the set of real numbers, then we might as well study real numbers. So in this lecture, we are going to speak about sets and relations, the set R, the algebraic and the order properties, and then intervals, inequalities, neighborhood, and finally Cartesian product. First, we come to the definition of a set. Why we define set? Because actually the set R is a set. So what's the meaning of a set? A set is a collection of objects that are characterized mainly by certain properties. It's a list of objects. And for example, they stick to a certain rule. Like for example, you say the set of even numbers or the set of prime numbers. Usually they are either finite or infinite. For example, the population on planet Earth is finite. Even if it is outnumbered. Yet, for example, numbers which are situated in the interval from 0 to 10 to the minus 3 is an infinite set. When you say x element in A, it means that x is one of the elements of the set A. For example, 2.5 is not a natural number. So you do not it by this symbol here, meaning that 2.5 is not an element in N. When you have a set A, and belonging to a universal set, like for example saying that A is the set of students who have succeeded, for example. So if you have a student, then it's either element in A, it's in the set of students who have succeeded, or he failed, or that X is not an element in A. These are the only two possibilities. Whereas if you have two sets, then, for example, students who have succeeded and students who own cars, then you have four possibilities then. Either X element in A and B, which is the lying in the set in between, or that X is in A but not in B. For example, they have succeeded but not who do not own cars. And for example, X not element A but element in B. They have failed but they own cars, etc. And then X neither they are element in A nor element in B. These are the only four possibilities that you have. In order that mathematicians, for example, George Cantor, in order to, instead of saying X element in A and not in B, etc., they have designed some sort of brief way of denoting intersection of sets and union of sets, and this is students are very well aware of this representation. It's kind of representation that allows you to set relations much more quicker than just saying X is here or X is there. So they define first the union of two sets, meaning that X either lies in A or in B. This is the shaded area like this, or that X lies in both A and B, which is the shaded area between the two sets, or that X lies in A but not in B, like this one here, the shaded area here. And this is very common that students know, and that A, for example, lies in the complement of A. For example, saying, for example, A is the set of students who have succeeded, and X belongs to A complement. That means the students have not succeeded. And then you have a kind of relationship relating the sets together. They're a kind of algebraic properties or algebraic laws, which are very familiar. One is very familiar with, like for example, saying that A union A is A. This is quite logical. Or A intersection A is also A. This is called independent laws. You may have some sort of commutation as well, like for example, A union B is B union A. This sort of laws we shall not wait long in order to explain them, because they are so logical and they're so known to students. These are some more algebraic laws of sets. These are properties called distributivity and identity laws. Like for example, A union phi is the null set, empty set. So naturally, since A either exists or not in A, so A union phi must be equal to A, etc. Now we come to the set of real numbers R. A real number, the set R is a set, and this is the special set that we are going to study our functions defined over this set. Actually, this set R is quite old. The disciples of Pythagoras, they knew about 500 before Christ that a number, for example, like square root of 2, cannot be put in the form A over B, where A and B are both integers, and we call it irrational. But worse than that, Euler discovered that there are numbers not only in the form of irrational of this sort, but they are also non-algebraic at all. We call them transcendental, like e or pi. In other words, they are not roots of equations, of algebraic equation, in which the coefficients are rational. And it seems now to be that the set R is composed of many sets. First of all, the set of natural numbers. This is the way we count our objects, 1, 2, 3, etc. This is called the set of natural numbers, and it's called under addition and multiplication. The set of integers. The set of integers it comprises the set n. Addition to it, the 0 and the negative numbers. In fact, negative numbers are odd a little bit. They are familiar with people. The ancient Chinese actually were aware of it in the before the century 200 before Christ. But it has been delayed, the use of these sets, of these numbers, because in fact there are a little bit of strange quantities. Like, for example, how come a product of two negative numbers give a positive number? And this is why in the Renaissance, in the Middle Ages, before the Renaissance, usually people used to write negative numbers in the form of positive numbers, but in red color. And this is from this comes the word "you are in the red," meaning that you are overdrafted, meaning that you are indebted to a bank. So you have a negative account into the bank. So instead of writing it minus, they don't do it yet. They write it in red. As to the number 0. This came a little bit later, and this is why Whitehead, the colleague of Russell, called it the most civilized number, because actually it arrived as last number. This is actually was known to the Hindus, was known to some tribes of the Mexique. Also, the Greek used to denote it by a circle and beneath a dash like this. But the Arabs, as a matter of fact, who were the first to use it in algebra, algorithms use it to solve equation of the first and second kind and second order by equating in his book he set an algorithm, he set a way, a method, a mechanical way by which one can solve the equation, and he used the 0. Also, the Arabs use it discovered what is called the positional form of numbers. Instead of using the Roman cumbersome notation of numerals, this is much more easier to just put 1 and then beneath besides it you put 0 means 10 or 2 zeros mean 100, etc. So in fact the number 0 came last. This 0, in fact, not only it's used in algebra, but the word itself, as a matter of fact, is Arabic. Of course, 0 is not Arabic as such, because it was known previously, but it's the Arabs who use it. And even the word 0 itself is Arabic. The word sifr and the word sifr was translated into zephyrum in Latin, and then 0. This is actually Arabic. And then comes the set of rationals. The set of rationals comprise the set of integers along with some sort of numbers which can be put in the rational form. In other words, it's closed not like Z under multiplication and subtraction and addition, but is also under division by a term not equal to 0. This is called rational. And it looks now as that the system R, or the numerals R, are seated on the real line like this, where each number is known its place, bigger or equal or less than other number, except some actually holes like this, some odd numbers like e, pi, square root of 2. And people actually thought, the mathematicians thought, that the majority of the numbers are the rational numbers, till they have discovered that, on the contrary, it's the irrational numbers which are actually have the majority of the seats. And they have actually defined a concept called countability, and they proved that rational numbers are countable, contrary to irrational numbers which are countable. First, they tried to divide numbers into categories. So they started by saying they are algebraic or not algebraic, transcendental. An algebraic number like rational numbers or square root of 2, for example. But then they got confused with some number. They didn't know where to put it. Either they're algebraic or not, and this is why they give up with this subdivision, and that can propose to divide numbers into two kind of numerals. Either they are rationals or they are irrationals, because in fact even the irrationals, like square root of 2, we use it in the calculator in the approximate form 1.414, etc., and pi 3.14, etc. And the set of real numbers then can be decomposed into two sets, either Q or R, but not Q, the rationals or irrational. This is actually the classification that is being used nowadays. So N is a subset of Z, and Z of Q, and Q of R, and still there is the complex numbers which de Moivre and Euler investigated, studied, and it's not actually important in our course here of calculus, because we study only calculus of real variables. Now we come to some properties of R. There are algebraic properties, and actually they are known. You know very well that 3 plus 4 is equal to 4 plus 3 plus 3. There is the associativeness. There is the existence of the zero, the existence of the negative. All these are very well familiar. These are called algebraic properties, and they apply to A numbers. A divided by A is equal to 1, distributiveness, etc. There is now the order properties of R. The order properties of R, in fact, we call R a complete order field. Why it's a field? Because it's closed under the algebraic operations. It is ordered because every number we know its place on the line, whether it's bigger, smaller, equal to another number. It's also complete because any non-empty subset of R has a least upper bound and greatest lower bound. And these are actually the transitivity. For example, you have if A is smaller than B, B smaller than C, it's logical that A becomes smaller than C, etc. All these the students are aware of. Now we can actually choose intervals or segments that are cut from the real line, and we call them intervals. These intervals, they can be open like this. They can be closed like this one. And we see now why they are called open and closed. This one is bounded. Why is bounded? Because it's less than B and bigger than A. X is allowed to vary between A and B, but it's forbidden that it becomes equal to A or B. This is bounded closed. This is unbounded, but it's half open because it's open from here and closed from here. And this is the same thing. From B it's closed, from A it's open. And then comes also another form. For example, this one is unbounded because it goes to infinity. And it's open. On the contrary, this is closed from A, but it's unbounded set. This one is also closed but unbounded, open but unbounded, and this one is closed but unbounded. And this set R, we call it closed and open at the same time. We'll see why in a while. Then come the inequalities. The inequalities are expressions in which because you know in relations in mathematics that we either have identities, like for example sine square of an angle plus cosine square is equal to 1, or we have equation like x square is equal to 2, from which x becomes plus or minus square root of 2. This is called an equation. And you have an equality. The solution of an equality yields sets, whereas the solution of equations yield numbers. Here, these are kind of inequalities, but actually they're kind of equalities with their look very much like identities. In other words, they're verified for all values of A and B. Yet, when you have an equality of this sort, like for example, you wish to solve an equality like this: x squared minus 3x minus 4 greater or equal to 0. What you do is that you factorize the equation into two expressions here, and you have either, since this is the product is bigger, larger, greater or equal to 0, then x minus 4 must be greater or equal to 0, and x plus 1 also. So it's like saying, for example, you have more than 1,000 euro and more than 4,000 euro, so you own more than 4,000 euro. So from this, x must be greater than equal to 4. And on the contrary, if x less than 4 and less than minus 1, so it must be less or equal to minus 1. And so this is actually the set which we obtain, which is the solution of this inequality. In other words, you obtain not a number, but a set. If you have an equality of this sort, like 2x minus 7 divided by x minus 2, how can we solve this inequality? Actually, we write it in this form, and then we try to study this fraction here. The best thing to do this is to, you wish to study when is x plus 1 minus x plus 2 is greater or equal to 0. What you do is you draw two lines like this. Here, the first one here, you got x plus 1. It's very well known that if this is minus 1, number minus 1, then x plus 1 is positive if it is x is greater than minus 1. Where it is negative, it is less than minus 1. And then you write here also, you write down here 2, and same thing applies to x minus 2, which is positive for x greater than 2. And if you divide the two signs one to the other, you obtain here, this is positive here, and in this part section it's negative, and then becomes negative by negative becomes positive, and this is minus 1, and this is 2. So in other words, when is x plus 1 divided by x minus 2 is greater or equal to 0? When x is what? When x lies in the interval from minus infinity to minus 1, and a union, we use the notation up to infinity. Of course, this is wrong here. Why? Because we cannot divide by 2. And therefore, we exclude 2. And then we get what? The open, unbounded interval from 2 to infinity. So this is the way how you do it. You start by drawing the line x plus 1 bigger than 0 and x minus 2. Greater or equal, of course, because you may include minus 1. But here you exclude minus 2 because you're going to divide by it. And finally, you obtain the solution of the sets. Now we comes to modulus. Sometimes actually we use the modulus to donate values. Like for example, the modulus of A. It stands for if it is positive when A greater or equal to 0 and negative A when A is less than 0. And these are very common relation which one knows very well. The modulus of AB is equal to modulus A times the modulus of B. When you divide A by B, you take the modulus. And B is not equal to 0. If modulus A is less than B, and this is actually used all the time, it means that A is either less than B or greater than minus A. Whereas if you have modulus A bigger than B and B is positive, of course, either A is greater than B or A is less than minus B. And finally, if modulus A is equal to B, it means just that A is either equal to B or A is equal to minus B. For example, if you have an inequality of this sort and you wish to solve it for x, the best thing to do is to square both parts, both sides, and then you expand here to reach such an equality. And now we come to an important concept, the concept of a neighborhood. The concept of a neighborhood is actually very important in analysis. Because, for example, suppose you are in the United States and you wish to know where is Rome. So what you do is that you have the map of the world, and then you say, for example, you want to know where is Pisa. So you say that Pisa is in the neighborhood of Rome. Why? Because it's very clear that they are so neighboring to each other. While you are in the United States and the map is with scale is small, so actually you directly realize that Pisa is very near to Rome. So you say that Pisa is a neighborhood of Rome. But while you are in Rome, you say that Viterbo, it's in the neighborhood of Rome, while Pisa is not in the neighborhood of Rome. So in fact, what we do is that we take a region around the point A, and this is the point at which one wishes to study the neighborhood of A, and you take all points that are at a distance less than a quantity epsilon. In other words, what you do, in fact, is that this is your neighborhood here. This is the point A at which you wishes to study the neighborhood. Any point x here is in the neighborhood of A. So you say x minus A is less than epsilon. And this actually radius here is equal to epsilon. In fact, you may have this neighborhood, and you may have another neighborhood which is called also deleted neighborhood. You can have this is bigger than 0. In other words, you exclude the point A. This actually is important when you study limits, because you may have functions that are defined in an interval, and you may have functions which have limits that are not defined at a point, and yet it has limit at a point. And this is why sometimes we use deleted neighborhood. In fact, neighborhood are very important when we study, yet we have said just now that why we consider, for example, an open interval and a closed interval. Suppose you have an interval, for example, from 0 to 1. This we call open, whereas this interval we call closed. Why we call this open and this closed? Actually, if we take the point 1 here, if you draw a neighborhood, you find that the point 1, we call point 1 a limit point. So a limit point to a set is a point in which, where if you construct any deleted neighborhood, it contains point of the set. And in fact, this point 1, it contains, yes, point in the set. So 1 is a limit point. Here also 1 is a limit point. of this set here from 0 to 1. But there's a difference here in between. Why? Because 1 is an element in the set, yet 1 here is not an element in the set. And this is why this set we call closed. Why is called closed? Because it contains all limit points. Yet here 1 is not a point in the set. And this is why we say that this set is open. So actually a set which is closed now is a set which contains all its limit points. On the contrary, sets which are open are sets that all the points are interior points. What is an interior point? An interior point is a point in which if you draw any neighborhood to this interior point, you'll find that it's contained completely in the set. For example, for this set, which is between 0 and 1, this set, suppose you take a number here, 1 minus epsilon. This is an interior point. Why? Because if you take a neighborhood of radius epsilon over 2, you end up with what? 1 minus epsilon over 2, which is less than 1. In other words, it's element in the set. So we see now that this is called an interior point. In other words, all points, interior points are points that all the neighborhoods of this point are contained in the set, while a closed interval is an interval in which contains all limit points. What about now the set R? Can we consider it closed or open? In fact, the set R can be considered both closed and open. Why? Because any point in the set is an interior point, and at the same time, R contains all its limit points. And this is why R is both closed and open. And the same time with phi, which is the null set, the empty set. Why? Because it's the complement of R. So actually, this is the neighborhood of a point A. We see here that it has radius epsilon. Yes. Before actually we leave the theme of closed and open sets, we wish to emphasize that since we said before that R is a complete order field in the sense that every non-empty subset of R has a least upper bound and greatest lower bound. What's the meaning of this? If we come again with the consider again the interval from 0 to 1. Now we said before that 1 is not element in this set, and this is why this set is open. Yet the other set here, for example, 0 to 1, this set is closed because it contains its limit points. The point 1, what about the point 1? How does it stand in regard to this set? In fact, any element in this set, sure, it's less than 2, for example. But what about 1? We call 1 the least upper bound of the set. We write it this way, LUB, least upper bound. Least upper bound, or sup. In other words, any point x here is always less than 1. Of course, we usually, when we write something like this, usually we don't know exactly where x lies. I mean, when we say a is less than or equal to b, usually we use this notation when we don't know a with respect to b. But when we know exactly the value of a and b, then we know exactly where do they stand on the line. So here actually x may vary between 0 and 1. So we call 1 a maximum bound, of course, because any value x does not ever exceed the value 1. But at the same time, the value 1, it's an upper bound. Yes, it's an upper bound for the set, but it's the least one. In other words, there is no other bound which is smaller than 1. How would you know this? The way mathematicians do it is that they say x is less than or equal to m. For example, this is the least upper bound. This is an upper bound now, but is greater than m minus epsilon. In other words, if you take any epsilon, a neighborhood, deleted neighborhood of the point 1, you will find always element in the set. So we call this least upper bound. And same thing when you say this is greatest lower bound. So it looks now as if every interval, in fact, it's cut from the real line, and it has an upper and lower bound, as well as a least upper bound and greatest lower bound. Usually sets. Sets. When you suppose, for example, you have a set, and this set you know very well that it's less than or equal to 5. Does it mean that x is equal to 5? We don't know. it may be less than 5 or equal to 5. It's like, for example, it's written on a tunnel, for example. It's forbidden, for example, that the height of the cars traveling into the tunnel may exceed as height 5 meters. If you are sitting on the other side of the tunnel, does it have to, do you have to measure the height, stop every car and measure the height of each car? No, you know very well that his height is less than 5. But what you are not sure of, that you may found a car that has passed through the channel and its height is equal to 5. And therefore, actually, when we write x is less than or equal to 5, it may be less than 5 or it is equal to 5. 5, in fact, if there are cars, here the set is finite because there are a number of cars. The set is finite. So we call 5 then, in this case, the maximum. Maximum because there exists a car which has 5 meter height. Same thing here when you have 1. Here 1 is the least upper bound to the set, and 1 also is the least upper bound to the set. But 1 belongs to the set. So we call the set maximum. And this actually applies to functions. When a function, for example, is determined, for example, at a point, reaches a point like this. For example, at 2x cubed, for example. X cubed at 2, it's equal to 8. But it's not equal to 8 because it's not defined at 2. But 8, as a matter of fact, in the range of the function, it's a least upper bound of the function f. Now we comes to the Cartesian product. The definition of Cartesian product actually was brought about by Descartes. We know Descartes is a French philosopher. He actually died early because of pneumonia, because he went to Sweden to apparently to teach some of the princesses there. This philosopher, he's the one to have proposed a Cartesian product of numbers. He's the one to have proposed the two axes, orthogonal axes x, y, whereby any point located on the plane can have an ordered pair or can have two coordinates. The Cartesian product, as defined for two sets A and B, of course they are non-empty, is an ordered pair A B, where A is element in A and B element in B. In other words, you take, for example, suppose, for example, you have an A is equal to, for example, the set 1 and 2, and B is the set, for example, -1 and 3, and you wish to calculate the Cartesian product AB. So what you take is that you take the set 1 with -1 and 1 with 3, and again 2 with -1, and again 2 with 3, etc. This is called the Cartesian product of two sets. Of course, if the set A and B are infinite, like for example you have something like this, for example this is the set A and this is the set B, so you end up with what? You end up with a rectangle where each element in this rectangle have two pair x and y coordinates, which they define if you take all the numbers x and y, all the ordered pairs x and y, you define a set which is called the Cartesian product of the two sets. For example, we have here two sets A and B. A is 1, 2, and 4, and B is -1 and 3. So the Cartesian product of these two sets is what? Is the set composed of all ordered pairs, 1 with -1 and 1 with 3, and again 2 and -1 and 2 and 3, and finally 4 with -1 and 4 with 3. This is the Cartesian product between two sets A and B. Of course, here the two sets are finite. This can be actually explained or exemplified using this kind of tree, whereas you have primary branches which relates to the elements of A, as they show here, A1, A2, or A3. And you have other secondary pairs, secondary set of branches that pertaining to the branches related to the set B. So if you want the Cartesian product of the set A cross B, what you do actually is to enumerate all these secondary branches. Because, for example, for this branch here, it's A1 times B1. and the set B comprises all the numbers from B1 to Bm. So A1 goes with B1, then A1 goes with B2, until A1 goes with Bm, and same thing with A2. So actually the numbers of secondary branches actually pertains to the overall A cross B. In fact, often with our relations, we are not really interested in all the Cartesian product of A and B. We wish to track those order pairs only confining or adhering to certain properties. Not all the Cartesian product AB. Like for example here, suppose for example that you wish to connect the elements of A with the elements of B. Now here is A and here is B. So the Cartesian product is what? The set of order pairs of A cross B, which are 6 elements or 6 order pairs. But you wish, for example, to consider only those order pairs in which the difference between X and Y is even, for example. So actually Y, 1 cannot go with 4. Why? Because 1 minus 4 is odd. So what you can do, you can take 1 with 1, which gives 0, or 1 with 3, which gives 2, is also odd. So actually you choose among the Cartesian product those only which have a property which called Q, and this property actually is a kind of arrows which emanates from A and ends at B in such a way that the difference between X and Y are only those which satisfy the relation that X minus Y is even. So the relation Q here says that necessitates that since X minus Y be even, then you start with first the cross product A cross B, and you get here the 6 order pairs, and then you choose among A cross B those Q which renders the difference between X and Y even. So actually 1 minus 1 is 1 and 1 is okay, because 1 minus 1 is 0. And 1 minus 3 is also okay, because 1 minus 3 is minus 2. And 1 minus 4 isn't. 2 minus 1 isn't also, because this gives 1. And 2 minus 3 also 1, which is unacceptable. So there remains 2 minus 4 gives 2. So you choose the order pair 2, 4. So you end up what? You end up here with 2 order pairs only out of the A cross B ordered pairs. And we call what? We call XRY, in other words, the relation Q. It's a relation of XRYX versus Y, which is a partial or a subset of the whole cross product or Cartesian product AB. And this satisfies a certain relation which you are approving of. You approve certain relation. And from this relation, you start to choose those which have only the property Q. So we say it in this way. We choose some of the order pairs from A cross B which satisfy the relation Q. Usually we represent such relation Q in the form of arrows. Arrows which emanates from A and end up at B, and which relates every X in A to every value in B such that Q is satisfied. Here Q stands for the relation which admits those values of those order pairs or those values of X associated with the corresponding values of Y such that X minus Y is even. So actually what we do, if, for example, in this case, since we require that X minus Y is even, we end up with these 2 sets here. We consider each set as a circle like this. This is a kind of diagram, Venn diagrams, in order to clarify the matter further. Here, this is the set A, composed of the 2 elements 1 and 2, and B of 3 elements here, 1, 3, 4. And then we have arrows emanating from 1, 2, 1, and 3 only. Why? Because this is the order pair 1 and 1 and 1 and 3, such that the difference between X and Y is even. And same thing with 2. With 2, we choose 2 versus 1 is unacceptable. Same thing with 2 and 3 also. So it ends up with 2 and 4. This is actually how it looks. This is the relation Q. We say that Q, the relation which assigns to every element in A another element in B such that X minus Y, or the element in A minus the element in B, is even. Suppose now that we wish to draw relation to investigate the relation Q such that Q is the relation which renders every x equal to y square, and such that x is element of the integers as well as z. In other words, the ordered pair xy belongs to the Cartesian product z cross z. So what we do, we start by the set Z, which is comprised all the set A, and this is the set B. Here we realize something, that x is equal to y square. So x equal to y square means that for every x there is 2 y's. Why? Because suppose x is equal to 1. If x is equal to 1, then y square is equal to 1. So in fact, what we do here, you have here a parabola. If x is equal to 1, it means that you have y is either equal to 1 or is equal to minus 1. So actually here the value 1 corresponds to two values in B. This is one drawback. So it's and there is another one also, another remark that we do, is that if x is equal to minus 1, which is an integer, it corresponds to y imaginary, because we cannot have a y such that y square is equal to minus 1. So actually now here we have two things very special to this relation Q, is that one value of x in A gives two values in B, and there are some values in A which do not, which there is no elements in B corresponding to this element, because minus 1, there is no such element in B corresponding to the element minus 1. So in fact, if in this example x, you remark that x equal 1 corresponds to two values in B, and x is equal to minus 1, there is no image in B. So in fact, if the following is satisfied, and this is important, if for each x in A there exists y in B, and there is an arrow emanating from every x in A, and also if this arrow is unique and ends up in unique point B, then we call that Q defines a function. And the set A is called the domain of the function, while the set B is its codomain. In fact, this is the subject we're going to discuss in detail next time. By then, we end up with this lecture. We started by defining real numbers until we end up with a relation and Cartesian product, and this is actually the basic subject which furnishes the detailed concept of function. I wish at the end to remind you that this lecture, as well as the preceding and the one that you're going to give in the next times, are all uploaded to the site MedNetU, administered by Nettuno, the consortium Nettuno of distance learning. And until then, until we meet again, thank you very much.